When we originally introduced pairs made out of consts, made by consts, we only said a few axioms about them, which were of the form, what were they? For all x and y, the car of the consts of x and y is x, and the coter of the consts of x and y is y. And these say nothing about whether a const has an identity, like a person. In fact, all they say is something sort of abstract, that a const is the parts it's made out of. And of course, if two things are made out of the same parts, they're the same, at least from the point of view of these axioms. But by introducing assignment, in fact, mutable data is a kind of assignment. We had a set car and a set coter. By introducing those, these axioms no longer tell the whole story. And they're still true if written exactly like this. But they don't tell the whole story, because if I'm going to set a particular car in a particular const, the questions are, well, is that setting all cars and all constants of the same two things or not? We used constants to make up things like rational numbers. There were things like 3 over 4. Supposing I had 2 3/4. Are they the same one? Or are they different? Well, in the case of numbers, it doesn't matter, because there's no meaning to changing the denominator of a number. What you could do is make a number which has a different denominator. But the concept of changing a number which has to have a different denominator is sort of very weird and sort of not supported by what you think of as mathematics. However, when these constants represent things in the physical world, then changing something like the car is like removing a piece of the fingernail. And so constants have an identity. Let me show you what I mean about identity first of all. Okay? Let's do some little example here. Supposing I define A to be the consts of 1 and 2. Well, what that means, first of all, is that somewhere in some environment I've made a symbol A to have a value which is a pair consisting of pointers to a 1 and a pointer to a 2. Just like that. Now, supposing I also say, define B to be the const doesn't matter, but I like it better. It's prettier. Of A and A. Okay? Well, first of all, I'm using the name A twice. At this moment, I'm going to think of constants as having identity. This is the same one. And so what that means is I make another pair, which I'm going to call B, and it contains 2 pointers to A. At this point, I have 3 names for this object. A is its name, the car of B is its name, and the coter of B is its name. It has several aliases, they're called. Now, supposing I do something like set the car. The car of the car of B to 3. What that means is I find the car of B, that's this. I set the car of that to be 3, changing this. I've changed A. If I were to ask, what's the car of A now, I would get out 3. even though here we see that A was the const of 1 and 2. I caused A to change by changing B. There is sharing here. That's sometimes what we want. Surely in the queues and things like that, that's exactly what we defined and organized our data structures to facilitate. Sharing. But inadvertent sharing, unanticipated interactions between objects, is the source of most of the bugs that occur in complicated programs. So by introducing this possibility of things having identity and sharing and having multiple names for the same thing, we get a lot of power, but we're going to pay for it with lots of complexity and bugs. So also, for example, if I just looked at this just to drive that home, the catter of B, okay, which has nothing to do with even the car of B, apparently. The catter of B, what's that? Take the cdr of B, and now take the car of that. Oh, that's 3 also. So I can have non-local interactions by sharing, and I have to be very careful of that. Well, so far, of course, it seems I've introduced several different assignment operators. Set, set car, set cdr. Well, maybe I just get rid of set car and set cdr. Maybe they're not worthwhile. Well, the answer is that once you let the camel's nose into the tent, the rest of him follows. Okay? All I have to have is set, and I can make all of the bad things that can happen. Okay? Let's play with that a little bit. A couple of days ago, when we introduced compound data, you saw Hal show you a definition of const in terms of a message acceptor. I'm going to show you even more horrible thing. A definition of const in terms of nothing but air. Hot air. What it is the definition of const of the old functional kind in terms of purely lambda expressions. Procedures. Because I'm going to then modify this definition to get assignment to be only one kind of assignment, to get rid of the set car and set cdr in terms of set. So what if I define const of x and y to be a procedure of one argument called a message m, which calls that message on x and y. Okay? This idea was invented by Alonzo Church, who was the greatest programmer of the 20th century, although he never saw a computer. It was done in the 1930s. He's a logician, I suppose, at Princeton at the time. Define car of x to be the result of applying x to that procedure of two arguments, a and d, which selects a. And we'll define cdr of x to be that procedure to be the result of applying x to that procedure of a and d, which selects d. Now you may not recognize this as car, cdr, and const, but I'm going to demonstrate to you that it satisfies the original axioms just once, and then we're going to do some playing of games. Consider the problem car of const of, say, 35 and 47. Okay. Well, what is that? It's the result of taking car of the result of substituting 35 and 47 for x and y in the body of this. Well, that's easy enough. That's car of the result of substituting into lambda of m of 35 and 47. Well, what this is the result of substituting this object for x in the body of that. So that's just lambda of m. That's because this object is being substituted for x, which is at the beginning of a list. Lambda of m of 35 and 47, okay, applied to that procedure of A and D, which gives me A. Oh, but that's the result of substituting this for m here. Okay, so that's the same thing as lambda of A, D, A, applied to 35 and 47. Oh, that's 35. That's substituting 35 for A and 47 for D in A. So I don't need any data at all, not even numbers. Okay? This is Alonzo Church's hack. Okay. Well, now, we're going to do something nasty to him. Being a logician, he wouldn't like this. But as programmers, let's look at the overhead. And here we go. Okay, I'm going to change the definition of cons. Okay? It's almost the same as Alonzo Church's, but not quite. What do we have here? The cons of two arguments, x and y, is going to be that procedure of one argument m, which applies m to x and y as before, but also to two permissions. The permission to set x to n, and the permission to set y to n, given that I have an n. Okay. So besides the things that I had here in Church's definition, what I have is that the thing that cons returns will apply its argument to not just the values of the x and y that the cons is made of, but also permissions to set x and y to new values. Now, of course, just as before, car is exactly the same. The car of x is nothing more than applying x, as in Church's definition, to a procedure, in this case, of 4 arguments, which selects out the first one. And just as we did before, okay, that will be the value of x that was contained in the procedure, which is the result of evaluating this lambda expression in the environment where x and y are defined over here. That's the value of cons. Now, however, the exciting part, Kutter, of course, is the same. The exciting part, set car and set Kutter. Well, they're nothing very complicated anymore. Set car of a const x to a new value y is nothing more than applying that const, which is the procedure of one argument, which applies its argument to 4 things, to a procedure which is of 4 arguments, the value of x, the value of y, permission to set x, the permission to set y, and using that permission to set x to the new value. And similarly, set Kutter is the same thing. So what you've just seen is that I didn't introduce any new primitives at all. Whether or not I want to implement it this way is a matter of engineering. And the answer is, of course, I don't implement it this way for reasons that have to do with engineering. However, in principle, logically, once I introduced one assignment operator, I've introduced them all. Are there any questions? Yes, David.
I can follow you up until you get, I follow all of that, but when we bring in the permissions, defining cons in terms of the lambda n, I don't follow where n gets passed.
Oh, I'm sorry. I'll show you. Okay, let's follow it. Of course, we could do it on the blackboard. It's not so hard, but it's also easy here. Supposing I wish to set Kutter of x to y. Okay?
Okay.
See that right there, set cooter of x to y. X is presumably a cons, a thing resulting from evaluating cons, right? Therefore, x comes from a place over here, okay, that x is of the result of evaluating this lambda expression, right? That when I evaluated that lambda expression, I evaluated it in an environment where the arguments to cons were defined. That means that as free variables in this lambda expression, there are in the frame which is the parent frame of this lambda expression, of the procedure resulting from this lambda expression, x and y have places, and it is possible to set them. I set them to an n which is the argument of the permission. The permission is a procedure which is passed to m, which is the argument that the cons object gets passed. Now let's go back here in the set cooter. The cons object, which is the first argument of set cooter, gets passed an argument. That is a procedure of four things, indeed, because that's the same thing as this m over here, which is applied to four objects. The object over here, SD, is in fact this permission. When I use SD, I apply it to y, right there. So that comes from this.
So what do you...
So at the n, so just want to finish that. The n that was here is the y which is here. Okay? How's that?
Right. Okay. Now when you do a set cooter, x is the value the cooter is going to become.
The x over here. I'm sorry, that's not true. The x is the set cooter has two arguments. The cons I'm changing, and the value I'm changing it to. So you have them backwards.
Okay.
That's all. Are there any other questions? Well, thank you. It's time for lunch.